last time we proved that the collection of even permutations is a subgroup of the collection of all the permutations. So one thing that I want to mention here is that this set of even permutations is called the alternating group of degree n. Degree n is because it has to do with the number of elements that is permutating. Now, so we're going to talk about a little bit more in this lecture about this subgroup of even permutations. But before that, let's do an example. So let's say we want to find all the elements of A3. So that's the even permutations on 3 elements 1, 2, 3. So let's look at that. So we already know that A3, the collection of even permutations, is a subgroup of S3. And one thing that we computed in another video was that the elements of S3 permutations on the 3 elements are the identity 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So these are all the permutations. So from here, A3 will be the ones that are from here that are even permutations. So the even permutations of S3 are, in this case, then the identity, because it's, the identity, of course, is an even permutation. And if you look at the other one, so this 1, 2 is odd because it's only 1, 2 cycle. This is odd, 1, 3, and this is odd. This one and this one, they are even. Because if you express this cycle and this cycle as a product of 2 cycles, then you will get 2. So it's going to be 1, 3, 1, 2, and this is 1, 2, 1, 3. If you do what we did before. So that will give us that this is the collection of the even permutations of S3. And that by definition is A3. A3 is the collection of even permutations of S3, and we proved already that this here is a subgroup of S3. So that means that if you operate this 2, you get again back another element of A3. So in this particular case, if you see, we have 3 elements in A3. So we have 1, 2, 3 elements. So A3 has 6 elements, and that's half of the elements of S3. S3 has 6 because it's 3 factorial. That's 6 elements of S3. Now, this is not a coincidence. The fact that A3 has half of the elements of S3 is not a coincidence because of this theorem. So this theorem says that if you have n bigger than 1, the number of elements of an, the number of elements of, or the number of even permutations is n factorial divided by 2. This is half of all the permutations in Sn. Now, I'm gonna prove this one, so because this one has a good idea in terms of set theory. All right, so we're gonna prove this theorem. We're gonna prove the set of even permutations has half of the elements of Sn. So to do that, I'm going to introduce some notation here. So let's look at this set. I'm going to call Bn the set of all the permutations in Sn that are odd. Now Bn, as I mentioned in a previous video, Bn is not a subgroup of Sn because it doesn't have the identity for one. And for second, it's not closed. If you operate 2 odd permutations, you get even permutations. So it's not a subgroup. But it is a subset of Sn. Now, the claim that I have here, which I'm going to prove, is that the union of the odd permutation and the even permutation is exactly Sn. Now, this proof is not going to be complicated, but I want to emphasize that. Now, the point of doing all of this proof is this number of elements is n factorial. So what we are doing in this proof is dividing the number of elements or the elements of Sn into even and odd permutations, and these 2 sets are actually the same number. So in Sn, you have the same number of even permutation and the same number of odd permutations. So the idea of the proof will come from there. All right, let's prove this claim. So let's look at the first part. So we need to show that this set is equal to this one. So I need to prove that this set is included in Sn and Sn is included in this set here. Now, we know that both An and Bn are both subsets of Sn. So if you take the union of two subsets of the same set, that of course is still included in the same set Sn. So A union Bn is included in Sn. Now if I choose the backwards one, it's meaning that Sn is included in these two, then that will be proof that these two sets are the same. So let's do the other part. So for the other part, I'm gonna prove that Sn is included in this union. And to do that, I'm gonna take an element here and I'm gonna choose that is in this union. So let's take an element in Sn. So we know by a theorem that any permutation is either even or odd, so we prove that. Then alpha is in An, so that means alpha is even or alpha is odd, so also alpha is Bn. But that is the same. This statement right here is the same as saying that alpha is in this set, in the union, because anything is in the union if it is in at least one of them. So that would prove that Sn is included in this one. So that means by 1, and this is 2 actually. This is number 2. So let me just erase this part. Let me call that one number 2. So that's number 2. So if you can see here from this statement and this one here, those sets are exactly the same. So by 1 and 2, the sets are the same. So that's proof of the claim. So the proof of the claim ends here. Now, there's another thing I want to mention here about the sets An and Bn. Those two sets An and Bn, they are disjoint. Disjoint means that have nothing in common. Or another way to say it is that the intersection is not empty. That's disjoint. Why is this? Because permutations are either even or odd. They cannot be both. You cannot have a permutation that is both even and odd. So these two sets have nothing in common. A permutation cannot be both even and odd. Okay, the second claim is that these two sets, An and Bn, have the same number of elements. So what I mean by that is the number of elements of An is the number of elements of Bn, so the number of even permutation is equal to the number of odd permutations. Now, one of the reasons I wanted to go over this proof is because it has an idea on how to check that two sets have the same number of elements. To do that, I'm going to recall this from set theory. To prove that two sets X and Y have the same number of elements, it is enough to prove that there is a bijection between the two sets. So there is a function that is one-to-one and onto from the set X into the set Y. If you can check that there is a function f that is a bijection between these two sets have the same number of elements. That is a fact from set theory. So every time you have two sets and you have to prove that they have the same number of elements, you in many cases you construct a function from one set into the other one. So let's do that. Let's construct that function here. So we'll construct a bijective function from the set of even permutations into the set of odd permutations. So if I have to construct a function, what I need to do is I need to say what happens with an element here. So if I take an element beta of An of even permutation, I have to map it into the set of odd permutations. So let's do this definition here. So let's define the function f acting on an arbitrary element of An like this. It's 1, 2, this 2-cycle composition with beta. Now, I can do this because n is bigger than 1, so at least I know that I have the elements 1 and 2. So we have this, that this is a permutation. Now, this permutation, if this function here is well defined, the result that I get from my f of beta, that result has to be here in Bn. So let's check that. The permutation 1, 2 is odd. Why is it odd? First of all, we are taking beta in An, so this is an even product of 2 cycles. So let's say, for example, this is 2k, and I have another 2 cycles. So I have 2k, 2 cycles, 2k cycles, and then plus 1. So 2k plus 1, that's odd permutation. So this is an odd product of 2 cycles. So what that means is that this function here is well defined. So meaning that if I take an element of An, doing the function like this, it's gonna give me an element of Bn. So the function is well defined. So what we have here. So this is the notation for the function here. Beta goes to 1, 2, 1, 2, and then beta. Now we need to check that this is bijection. Bijection means it's 1 to 1 and on to. So let's check 1 to 1 first. So let's check that f is 1 to 1. Let's recall the definition of what a 1 to 1 is. So we need to prove that whenever I have f of beta of 1 and equals to f of beta of 2, then beta 1 is equal to beta 2. This is the formal definition of 1 to 1. So assuming that these f's are the same, we have to put that the betas are the same. So let's do that. Let's assume that these two are the same. Now, by the definition of the function f of any beta is 1, 2 multiplied by that beta. So this one here evaluates to this one. Same for this other part here. F of any beta is 1, 2 times that beta. So that's going to be again the definition of this part. Now, we are in a group. We are in Sn. So left cancellation is something that we can do here. So if you do the left cancellation here on this side and this side, then you get that beta 1 is equal to beta 2 by left cancellation in group because we are in Sn. So that proves that this function right here is a 1 to 1 because we proved this statement. Now what is left to prove is that this is onto or surjective. Now let's recall a little bit what surjective means. Surjective means that whenever I take an element in the codomain, gamma, then I can produce an element in the domain that maps into that element that I'm calling gamma in this case. So let's take an arbitrary gamma in beta n, and I'm going to prove that that gamma comes from some element in an. So gamma here means that that gamma is an odd permutation. So that is, gamma is an odd permutation, just what I said. Now, if gamma is an odd permutation, that means 1, 2, gamma is an even permutation by the same argument that I used before. This is odd. So this is a product of odd 2 cycles. So let's say it's 2k plus 1 cycles and 2k plus 1 plus another 2 cycles, 2k plus 2. So that will give me an even permutation. So that's going to be even. Because it's even, this permutation is in AN, because AN is the collection of all the even permutations. Now, we claim that this is the element that gets mapped into gamma. So let's see that. So if we apply the function f to this element that is in the domain, 1, 2, gamma, remember what the definition of f is. F applied to any element of AN is multiplied by 2 on 1, 2 on the left. So this is the element and multiplied by 1, 2 on the left. So we get this. This is just by the definition of the function. But 1, 2 and 1, 2, these two cycles are inverses of each other. So 1 goes to 2 and 2 goes to 1. So this is fixing 1 and it's also fixing 2. So this is the identity. So that's going to give me just gamma because this here is just the identity. So that means I can produce an element in AN, which is this one here, that maps into an arbitrary element of Bn. So that shows that this function is onto. So what's the conclusion of all of this? We showed that that function, the way we define it, is a function from AN to Bn. In this case, let me write down the Bn there. Bn. That function is a bijection. Because it's a bijection, then the two sets, AN and Bn, they have the same number of elements, so meaning that the number of elements of AN is equal to the number of elements of Bn. Now, this is going to be important for the proof. So we are almost done here with the proof. So we know, we already proven the claim that all the permutations is the even permutations together with the odd permutations. If that is the case, the number of elements here is the number of elements in this side. So the number of elements of Sn is the number of elements of this collection. Now, the number of elements of the union is the number of elements in the first one and the number of elements in the second one. That is a property that we can apply because AN and Bn are disjoint. This is very important. If AN and Bn are not disjoint, we cannot claim that these two are equal. This one is equal to this if and only if the intersection between AN and BN is the empty set. Otherwise, it's not. But in this case, we already said that these two sets, AN and BN, are disjoint. So this, the number of elements of this union, is the number of elements here. But there's one more thing I want to apply here. This, the number of elements of Bn, is exactly the number of elements of An, because that's exactly what we prove here. The number of elements in Bn is the number of elements of An. So this I can replace this one with the number of elements of An. So in this case, I have this number plus this number, so it's going to be twice that number. Now, but remember where we coming from. So the number of elements of Sn here is twice the number of elements of An. So the conclusion we can make from all of this sequence of equalities is that the number of elements of Sn is twice the number of elements of An. But we know, we prove this, that the number of elements of Sn is n factorial. So that means if I replace that here, this one is n factorial. So we will have that n factorial is equal to twice the number of elements in An. And then you can solve this here for the number of elements of An. So divide by 2 on both sides, and you can get that the number of elements of An is n factorial divided by 2, and that will finish the proof of that theorem. So we also have a way to find the number of elements of the even permutation. This n factorial divided by 2 is also the number of elements of odd permutations, because odd permutation and even permutation have the same cardinality. They have the same number of elements. So let's look at an example, a quick example here to emphasize that theorem. So let's say we want to find the number of elements of A5, which is how many even permutations are in S5. So by the theorem, the number of elements of A5 will be n factorial, and here is 5 divided by 2. 5 factorial is 120 divided by 2, that's 60. So what we can conclude from here is that there are 60 even permutations in S5. Now, list all of this might take a long time, but we know that there are 60 of them. All right, so that's all I have to say for this video. Take care and good luck.